Hey guys, Cooperific here. Welcome to the introduction to organic chemistry. Yay! So, in this video, we're going to be talking about drawing structures of organic compounds. So, this is one of the 4 videos that we are going to be addressing for organic chemistry. First is drawing of organic compounds. Second will be isomerism. Third will be the hybridization of atomic orbitals, and lastly it will be the free radical substitution of alkanes. So when it comes to drawing of the organic compounds, drawing structures of organic compounds, we'll be talking about the IUPAC rule. And the IUPAC rule states that in every organic compound you name, it will always contain these 3 important parts. So it will be the prefix, stem, and suffix. So for prefix wise, it will be mentioning about the name and the positioning of the substituent. The stem will be the number of carbon atoms in the longest chain, and the suffix will be the name and the positioning of the functional group. So just like in a video game and in a sports game, there will always be rules, right? So in naming and drawing organic compounds, they also have their own rules too. So first up, there are these 2 important punctuations you need to know. In sentences, you use them. In organic chemistry, you use them. So for hyphens and commas, hyphens, they used to be separating numbers and words when you name the organic compound. And then commas is to separate the number in the name of the organic compound. I can give you some examples later to illustrate what I mean. Then the substituents always must be in alphabetical order. The fourth rule is that these 4 special substituents, methyl, amine, hydroxy, and carboxylic acid, those groups, right? It can be written and drawn in the reverse order. So in the sense that the order of the atoms can be reversed. So example, for CH3, it can be H3C and with a single bond to the right. For ethyl group, only these are the 4 groups of substituents that you can reverse the order, and one group that you can't reverse the order is ethyl group. So in this case, this is correct, this is wrong. Yeah, this is wrong. Okay. Then the 5th rule is that when you are drawing the bonds between atoms, you must draw it in the sense that the atoms are correctly bonded to the correct atom. So for the central atom, it must be bonded to the carbon in methyl. For the central atom and it must not be bonded to like the hydrogen in methyl group. Okay, next up we're going to talk about the stem or the parent molecule. So in the parent molecule, there'll be the respective stem names for the number of carbon atoms. So to make it easier for some of you to remember, you just need to know that from 5 onwards, they are all the geometrical names. So it'll be pentagon, hexagon, heptagon, octagon, nonagon, and decagon. But for the first 4 rows, those are special. Those is only applies for the parent molecules and to name the number of carbon atoms in the longest chain. So if they are mass, s, prop, and build. For prefixes wise, there's a separate numbering system, so I will address that later. Then for cyclic compounds, like cyclic alkanes, whereby the atoms are arranged in the closed chain. So for this case, you need to make sure that you have this cyclo, yeah, then cyclo, yeah. So in this case, it's a hexane, 1, 2, 3, 4, 5, 6 carbons. So you should not just name hexane, you must put a cyclo in front. So cyclohexane. Then for suffix wise, you need to know the name and the positioning. So for naming these functional groups. There are these different, this is the list of some of the functional groups you need to know. It's just carboxylic acid, there's the esters, alkyl, chlorides, amides, nitrile, and so on. So if you just need to know the structure and the naming. So like oic acid, OH, OL, chloride, amide, and so on, and the structures. Those are the important things you need to know. And if you guys have a bit of hard time trying to remember, so one thing to help is that for the first few rows, except for nitrile, so like 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. These 6 functional groups, they will always have this C double bond O. So there will be this C double bond O, and then there will be an additional bond which carbon is bonded to. So for example, carboxylic acid, OH is the extra bond that carbon is bonded to. Ester will be O. Alkyl chloride will be obvious, the chloride there, so the one extra bond is chloride. Amide is NH2. Nitrile, okay, wait, other than the nitrile first, then aldehydes, there will be this hydrogen bonded to the carbon, and then ketones, usually there will be a carbon here. There will be 2 carbons at the sides. So, okay, for nitrile, one way to remember is that Ni, it will be for nitrogen, and then tri is triple bond. That's how you get carbon triple bond nitrogen. Okay, then another thing to know is that the first 6 rows, except for esters, the carbon atom is always numbered 1. And then ketones, it will not be on the first carbon atom because in the case of propane, as you can see, the first is not the first carbon atom. So this ketone right here is on the second carbon atom. Yeah, and then there will be the surrounding carbon atom at the side. Sorry, the surrounding methyl groups at the side. Then for prefixes, these are the following substituents. So this is the list of substituents. There will be your halogens, and then the stars ones are the slightly more difficult ones to remember. So there will be the cyano, C triple bond N. As you can remember, is similar to the functional group that you have remembered earlier, which is nitrile. There will be the oxo, C double bond O, and then so just remember is C double bond O and not a plain O oxygen bond. And then nitro will be NO2. So NO2 wise, there must need to remember there's a dative bond. So the dative bond, okay, so hold on. To visualize, it must be in a sense that because nitrogen would donate a lone pair of electrons to the vacant energetically accessible orbital of the oxygen atom. And then if it's a single bond wise, if you change it to a single bond, then oxygen 1, 2, 3, 4, 5, 6. Oxygen has 6 valence electron. If you have this nitrogen at 1 here, then it will not fulfill the stable electronic configuration. Yeah, so that's why there's a dative bond right there. Amino is NH2, and then one thing to note is that for number of substituents, for number of substituents, there's a special numbering system. So if there's 2 fluorine atoms, you must name it difluoro. Trifluoro, tetrafluoro. It's separate from the numbering system you have seen for the parent molecule, whereby you should not name it like S-fluoro, propfluoro, or butefluoro. Yeah. And then from 5 onwards are the geometrical numbering system. Okay. And then for mono is quite rare, you can choose to leave out the mono because it should be okay. It won't be ambiguous. Okay. Okay, this is one of the examples that I'm gonna lead you for. So first thing when you see this organic compound, yes, it's a very long name, but let's go step by step. So remember I told you there's 3 parts. So we'll start with the stem first. And what does the stem tells you? Pent. So pent, it means 5 carbon atoms in the longest chain. Yeah. Then next up we have the suffix. For the suffix, it indicates the functional group. And this is an alkene. So it's a C double bond C. And this number here indicates it's on carbon 1. So this is on carbon 1. And then for the prefix, there's this dichloro. Dichloro means that there is 2 chlorine atoms. So one is on carbon 1, another one is on carbon 4. Ethyl. So for ethyl, it is CH2CH3. Okay, so and it will be on carbon 3. Methyl, it will be CH3, and this will be on carbon 2. Okay, another thing before I draw the organic compound, the structure, remember what I talked about hyphens and commas. So if you were to name a organic compound like this, you should not leave out the commas and hyphens. All right. So when example for this hyphen, so it's to separate these 2 hyphens, separate the number and the words. These 2 hyphens separate number, word, and same and so on. And then for this comma right here, this is to separate the numbers. So this is to separate the number. So it will mean that one of the chlorine atom is on carbon 1, one of them is on carbon 4. Okay, then we'll just draw out. So 5 carbon atoms, 1, 2, 3, 4, 5. You can name the number of the carbon number in any order. From left or right is okay. Then next up is the functional group alkene. So there will be this double bond here. And then we deal with the dichloro. So dichloro, there's 1 chlorine atom on carbon 1. Carbon 1 and carbon 4. So carbon 4. Then there's the ethyl group on carbon 3. So carbon 3, it will be, my bad. Oh my gosh, that's a miracle! Oh, thank God, thank God. Okay. I thought my computer crashed again. Okay. So ethyl group on carbon 3, methyl group on carbon 2. So, and then what you do next is to fill up the rest of the organic molecule with hydrogens, such that each carbon has 4 atoms. Sorry, 4 bonds. Yep, correct. Okay, I need to draw this. Alright. Okay, maybe to make this more nicer, okay, I can't rotate it, but yeah, in this case, this is how you draw the structural formula for this compound. Okay, then in this case, I can actually also do it in this way, so ClH also. But what I want to talk about is there's different ways to represent the structures of organic compounds. So these are the 5 ways. Structural formula, condensed structural formulas, displayed formula, and skeletal formula, and stereochemical formula. So for structural formula, it's just the basic showing of bonds and group of atoms. So in this case, for this example right here, I'll go step by step. Butane is the parent molecule, so there's 4 carbon atoms. Then there's the suffix. The suffix shows that it's an alcohol group on carbon 2. So if I name my number 1, 2, 3, 4, can also number it vice versa, it will be here. This OH group is here. Then let's deal with the prefix. There will be the chloro on carbon 1, and then there will be the dimethyl on carbon 3. So there will be 2 methyl groups on carbon 3, CH3 and another CH3. And then fill up the rest of the molecule with hydrogen atoms such that each carbon has 4 bonds. Okay, so this is structural formula. As you can see, I showed the bonds of the molecule and also the fact that some of them like OH, CH3 and CH3, those groups can just leave it as it is, and you do not need to show out the bonds for those. So in a sense, structural formula is quite laid back lah. Condensed formula. In a sense, condensed formula is, I would say, the arrangement of different groups of atoms, but it's something similar to like your molecular formula, but it's to show the arrangement of different group of atoms. So in this case, we can deal each group by each group. So if example we're talking about carbon 1, right? There's the first carbon. Yeah. So first carbon, there's 2 hydrogen and 1 chlorine. So when you draw, so it's CH2Cl. Okay. Then second one will be CH, and then a OH group. And this OH group you must bracket. You must have, for condensed structural formula, the brackets are to show the substituents. And you can leave out the bracket at for some cases. So if example the OH group is at the end of the carbon chain, so in a case of OH here, then you can leave out the bracket when you write OH at the end. My bad. Okay. Okay, then afterwards, we deal with the third carbon. So the third carbon wise, I can represent this in a certain way. So notice how there's actually 3 methyl groups surrounding that third carbon there. So there's the one on top, bottom, and the right. So in this case, I can write it as CH3 3. And this is your condensed formula. Okay, then the split formula. Two things you need to take note wise is the relative placing of bonds and atoms, and you need to show all the bonds. Okay, so for the split formula, wise C, there's a Cl here. So methyl and your methyl groups, right? You must show every single bond. So all the CH bond must come out in the thingy. Yeah. Alright. When we are talking about relative placing wise, so if you know that carbon has 4 bonds surrounding it, so in this case, it's always be shown at a 90-degree. Even though in real life, you know that there's these 4 bond pairs, right? And it will be in the shape of a tetrahedral shape, and you know tetrahedral shape is usually 109.5 degrees bond angle. But for this case, displayed formula, your relative placing will be a 90-degree if there's a 4 bond surrounding carbon. Then another type of relative placing you'll need to take note of is ethane, or like any double bond where there's a trigonal planar. So if there's a trigonal planar, you need to know that it must be 120 degree, just like the bond angle of trigonal planar. Okay, then for skeletal formula, what you need to take note is to remove all the C and H atoms. Remove CH bond, leave out the CC bonds, and to know that every band and also the end of the line represents a carbon atom. So in this case, I will draw the longest chain. So there's 4, 1, 2, 3, 1, 2, 3, 4. So you see here, 1, 2, 3, 4. Okay, then there's a chlorine atom. We're gonna use the structural formula as a reference here. So there's the chloro here, and know that this N does not represent a carbon atom. This N right here doesn't represent a carbon atom. Instead, it represents the chlorine. Whereas this one, because there's nothing here, this one you can say that this is a carbon atom right there. So in the first carbon is just chlorine. Second one, you will have a OH group. Right there. Then the third one, you have 2 methyl groups there. What I'm gonna do right here is to show you that actually, oopsies. So this is the third one. And then these are the 2 methyl groups at the bottom here. Yeah. So just know that when drawing skeletal formula, if it's carbon atom surrounded by 3 bonds, except for the H, like the imaginary H, if there's a 3 bond, example, this second carbon is bonded to the first carbon, third carbon, and the OH, right? Then you show a trigonal planar. If it's a carbon atom bonded to 4 different groups, like here in carbon tree, then you would somewhat show a tetrahedral shape in a sense. You may not see it wise, but it looks like a tetrahedral. So yeah, tetrahedral. If you rotate it around. Partial skeletal, for this case, is if you want to show, this one is like also a bit laid back also, so it's just basically showing the we call that the methyl groups. So in this case, you show at the ends the methyl groups. Yeah. But honestly, the skeletal formula, not really. I would say I would prefer to draw the skeletal formula first. So yeah. Then stereochemical formula. This one will be a bit tricky, so I'll use another example. So for this example, so for 2-chlorobutane, longer chain is 4 carbon, chloro is on the second atom, fill the rest of it with hydrogen. Such that each carbon has 4 bonds. So in this case, for stereochemical formulas, usually it's always when you're gonna draw, for instance, enantiomers. For enantiomers wise, it's always about the chiral carbon. So there will be chiral carbon and is optically active and doesn't have like it has non-superimposable mirror images. So for this case, right, to show you how the stereochemical formula works, so this is chiral. Chiral because it has 4 different groups. There's a methyl group, the chlorine group, the hydrogen atom, and then there's the ethyl group. Ethyl group, I can represent it as CH2, CH3. So in this case, I have the mirror. This is the mirror, the dotted line. This dotted line. And then the chiral carbon, you need to label it with an asterisk sign. And then it will need to be in the shape of a tetrahedral shape, whereby you have your sash, and I will call it the wedges and the sash, the dash and wedges. So make it mirror. In a sense, you need to make it like a mirror. So then it will be CH2, CH3. The ethyl and the methyl group can be placed, and we can switch positions, but as long as the positioning, the spatial arrangement of these atoms is correct, in a sense that this chlorine is right here, this chlorine right here, cause it's a mirror. This one is here, this one is here. In a sense, both atoms must be in a mirror image. That is what is the most important for enantiomers as stereochemical formula. Okay, yeah, that is it for drawing organic compounds. Okay, so yeah, hope this clarifies everything. So I'll see you all in the next video.